natural numbers which starts from 1, 2, 3 and so on. The next system we have studied whole numbers where the number 0 has been added. We started with number 0. Then as we had grown for our classes, we have come up our classes. Then we had introduced or we have studied a new system, integers, where the numbers have signs like minus, like we have -3, -2, -1, 0, 1, 2, 3 and so on. Then again, in the next class what we have seen, we have upgraded to one more number system known as rational numbers. What are rational numbers? Rational numbers are numbers which are expressed in the form of P by Q, where Q not equal to 0. What does it mean? It means that there can be any integer. P is an integer. We all know Z represents an integer system. Q not equal to 0. Q should not be 0 at any point of time. P will take any of the integer, either any negative integer or any positive integer. So now we can say that all the numbers which are in the form of P by Q, where Q not equal to 0, are known as rational numbers. Example, let us see some examples. What is the example? -3, -7 by 2, 9 by 4. But see in this example. In these examples, we can see that none of the denominator is 0. So these systems are known as, the system of numbers are known as rational numbers. We have seen these rational numbers in our lower class, and we have seen some properties of these rational numbers in our lower class. The first property we have seen with our rational numbers is addition. With an addition, when two rational numbers are added, we get again a rational number. You can take examples. We can have 4 by 3, it's a rational number, plus 7 by 2, it's again a rational number. How do you add two rational numbers? We'll first take the LCM. LCM of 3, 2. We all know that LCM of 3, 2 is 6. So 6. Now change the numerators. We know that 3 into 2 is 6. So we'll multiply the numerator also with 2. 4 2s are 8. 2 3s are 6. So 7 3s are 21. So the sum of these two rational numbers is 29 upon 6. Again a rational. Similarly, we can have one more example. Like if I take -3 by 4, this is one rational number. And you take another rational number, 5 upon 7. When we know that if I add two of the rational numbers, always LCM 28, 4 and 7. So 4 into 7, so -3 sevens are 21. 7 into 4, 28, so 5 4s are 20. We all know when one number is a number with a negative sign and one number is a number with a positive sign, we will be subtracting them, and the number with the greater number, that sign will come. So it will become -1 upon 28. Again, it's a rational. So we have seen that when you add two rational numbers, you will get back one more rational number. Similarly, if you subtract two rational numbers, you will get a rational number. Multiplication of two rational numbers is a rational number. Division of rational numbers is a rational number. That's what we have seen in our lower classes. When we come to class 9, what is a new system we are going to learn? That is Irrational numbers. So again, what's happening? Irrational numbers are those numbers which cannot be expressed in terms of P by Q. Irrational numbers are those numbers which cannot be expressed in terms of P by Q. That is, square root numbers are irrational. So what are the examples for them? Square root of 2, square root of 3, square root of 7, square root of 17. So all these numbers which cannot be expressed as P by Q are known as irrational numbers. Now many students have some doubt that why can't we write square root of 4? Children, square root of 4. 4 is a perfect square. So square root of 4 is 2 and this 2 can be expressed as 2 upon 1. So what is happening? This is expressed in the terms of P by Q. So this square root of 4 cannot be an irrational number. Those numbers which cannot be expressed in terms of P by Q are known as irrational numbers. So the examples are root 2, root 3, root 7, root 17 and all. Now we will see some of the properties of irrational numbers. When do we call irrational? If we add two, say, irrational numbers like root 3 and root 5, again you are going to get an irrational number. If two irrational numbers are added, we will get back an irrational number. The next one is, if you are adding one rational number and one irrational number, you are going to get back an irrational number. Root 2 plus 7. Let us take this. We all know that square root of 2 is 1.41 and you added plus 7. It is becoming 8.41. So again, root 2 plus 7 will become an irrational number. One number rational, and if you are adding one more irrational number, it's becoming an irrational number. If you are subtracting one irrational number minus an irrational number, the result will be an irrational number. If you are multiplying one rational number by an irrational number, 4 is a rational number here, root 3 is an irrational number, this 4 root 3 is again an irrational number. So, and if two irrational numbers are multiplied with each other, that is root 5, root 7, then again you will get an irrational number, root 5 into 7, which can be said root 35. For example, now here we will discuss one important property of an irrational number. Root a plus root b. This is, you have to calculate the square root of a completely, square root of b separately and then add. You cannot write this as root a plus b. That is, your root a plus root b will never be equal to square root of a plus b. But the same thing, when you are doing multiplication, root a into b, you can write it as root a into root b, or vice versa you can say root a into root b can be written as root ab. So this is an irrational number. And after this, we will see one more concept known as terminating decimals and non-terminating decimals. Terminating decimal. What is a terminating decimal? Terminating decimal is whenever you are dividing, a rational number is there, for example which is in the form of 7 upon 8. When you are dividing 7 by 8, if the remainder is not 0, we call it, if the remainder is 0, we call it as a terminating decimal. Repeating again, if you have a rational number like this, 7 upon 8, and you are dividing 7 by 8, if the remainder becomes 0, the decimal, this is known as a terminating decimal. For example, let us take an example like this, 20 upon 5. Now 5, 20, 4 times 20. The remainder is 0. Then the 20 upon 5 is a terminating decimal. Then if it doesn't terminate, then if the remainder is not 0, we call it as a non-terminating decimal. If the remainder of any number is not 0, we call it as a non-terminating decimal. For example, let us see the number 5 upon 6. Now dividing 5 by 6. 0, we all know, we'll put a 0, 0.6, 8s are 48, 10 minus 8, 2, again 0, 6 2s are 6, 3s are 18, minus, again 2, again 0, 3, again 18, again 2, 0. What is happening? The remainder is never becoming 0. When the remainder never becomes 0, this will become non-terminating decimal. What is happening? It is 0.8, 3, 3, 3, 3, 3, 3, 3 and so on. So now how can I write this 0.833 in decimal form? So if anybody writes like this 833 and put a bar over double 3. Non-terminating decimals. We will have more discussion on non-terminating decimals right now. Non-terminating decimals, for example, I write two problems here. Like if there is a decimal like 1.1642314 like this. It's not going to terminate at any point of time. Rather it is going to go like this. The division will never become 0. So the quotient is becoming like this 141 and so on. This type of decimals we have one type of non-terminating decimals. One type of decimals we have 1.166666. 6 will get repeated several number of times. It will not terminate at any point of time. Now these non-terminating decimals are also known as recurring decimals. We call them as non-terminating recurring decimals. Recurring means one number being repeated several number of times. Now if any particular, the second example, here only one digit is repeating. Then how do you represent these recurring decimals in the decimal expansion? How do you represent them? When as soon as we write any number, how to make it out that it is a recurring decimal and which digit is getting recurred every time? That we will see now. For example, see, there is a number 1.44444. What does it mean? 4 is being repeated several number of times. Now this, if you write like this, if you come across a number like this, there is a bar over 4. There is a bar over 4. If we notice, there is a bar over 4. What does it mean? That 4 is a point number which is going to be repeated several number of times. If we come across a number like 414, 14, again 14 like this, then what is happening? 41, 41, 41, 41. So if I write it like this number 1.41, what does it mean? That 41, 1, then again 41, then again 41, then again. So the recurring decimal decimals we can make out as soon as we write the number or we come across the number by just seeing the bar. Where is that bar located? If it is on the single number, only it is on that number is going to get repeated. If it is placed on the top of two numbers, then it will go, those two numbers will be repeated. One thing we have to remember is this is a recurring decimal. So we will come across these digits only after the decimal point. We will never come across this before the decimal. That is the integer part we call. That will not be repeated many times. But the numbers or the digits after the decimal point get repeated several times, and it is known as recurring decimal, and we can come across, we can decide it by seeing the bar on the decimal point, after the digit after the decimal point. If it is only on one number, only one number is going to get repeated. If it is on two numbers, the two numbers are going to be repeated. It can be at any point of time. Like for example, you can have 2.51, then 7 can get repeated several times. So that if you come across any number like this, this means it is 2.51777777. So it can be at any point of time. Need not be that it should be an immediate digit after the decimal, or it should be a second digit after the decimal, nothing like that. It can start at any point of time. So these are terminating and non-terminating decimals, and now we will see how to convert this decimal expansion into a rational number. Let us see with an example. For example, I am having a decimal expansion 0.6. A decimal expansion 0.6. If you see this, there is a bar on the top of 6. That means 6 is going to be repeated several times, an uncountable number of times. Now how to convert this recurring decimal 0.6 into a rational number? What's a rational number again? A rational number is a number which can be expressed in terms of p by q where q not equal to 0. So the procedure is like this. Let us say that this number is x, and let us write it as 0.6666 and so on. Now, since this 6666 is a decimal repeated digit, we will be transferring one digit after the decimal to the integer part. To do so, we will multiply this equation by 10. We all know that if we multiply by 10, one digit will move to its integer part, to the left part. If you are multiplying by 100, then 2 digits. If you are multiplying by 1000, 3 digits, and so on, we have learned in our lower class. So now, multiply by 10 on both sides. Then what will happen if you multiply by 10 on both sides? This will become 10x, and this 6 will move this side and it will become 6.6666 and so on. Let us name these two equations. This as the first equation and number this as a second equation. Now we are going to subtract 1 from the second equation. 2, 1 from 2. Equation 2. So now what will happen? 10x is equal to 6.666 minus x is equal to 0.666. We can write like this. 10x minus x, it is 9x, and this will become 6. All the decimal points will become 0. 6 minus 6, 0, 6 minus 6, 0, 6 minus 6, 0, it will go on. 9x is equal to 6. So now you can write x is equal to 6 upon 9. What is 6 upon 9? You can get it to more simplest form. 3 2s are 3 3s are. So it is x is equal to 2 by 3. So 0.6 recurring decimal expansion can be denoted as x is equal to 2 upon 3, which is a rational number. Which is a rational number. Now we can go on doing so many problems, so many decimal expansions like this using this procedure. Thank you.